Hello, I'm Aknur Karabay, Research Assistant at the Institute of Smart Systems and Artificial Intelligence, and in this video we'll cover Least Squares Regression. Let's assume that we are given the data on how product sales of a company depends on the temperature. And now, having this data, we need to make sales estimates. But as we see, the data is missing for some temperature values, and one way to overcome this issue is to find the approximate sales for those missing temperatures. To find an accurate approximation to those missing values, we need to find the model that will describe accurately the data, so it's always a good idea to plot the data to see the trend. As we see, the trend is linearly increasing, and a line can be fitted by trial and error. However, our target is to find a line with minimum average offsets from the data points, and in order to minimize the errors, we can apply Least Squares Regression. Least Squares method determines the best fit for a set of data points by minimizing the sum of the offsets or residuals of points from the plotted curve. The method was invented by German mathematician Gauss in 1795. Least Squares Regression is used to predict the behavior of dependent variables. In general, x-axis represents the independent variable and y-axis shows the values of dependent variable. Why it's called least square and how does it work? To answer this question, let's focus on the highlighted section. The vertical distance between the data points and the curve is called the error. The objective is to minimize the sum of square of the errors. That's why the method is called least squares. This method is very sensitive to outliers. A value that deviates a lot will pull the line toward it. Least Squares Regression can be applied to both linear and nonlinear dependencies. To better understand Least Squares Regression and mathematics behind it, suppose we have a dataset consisting of n samples, where x is the independent variable and y is dependent variable. Now, we choose a function f with m parameters to fit the dependent variable. Least Squares Regression tries to minimize the total squared error and mathematically denoted as follows. First, we need to find the offset between the original dependent variable and approximated dependent variable. Next, we raise it to the power of 2, such that we can treat both negative and positive offsets equally, and then we sum offsets for all sample points. As we have mentioned, to fit the data, linear and nonlinear functions may be applied that have a number of different parameters. And by setting the gradient of total square error function with respect to these parameters to 0, we can find the minimum total square error. As a numerical example, let's consider the problem with sales analysis we have seen, which can be described by a linear function. The linear least squares regression line is defined as follows. f of x is equal to b0x plus b1, where b0 is a slope and b1 is y-intercept. By substituting the equation of least square regression by the equation of the line, we can get the final equation of total square error. The equation of line accommodates two constants. The first one is the slope and the second one is y-intercept. And to find the minimum total squared error, we need to find the values of those parameters that will satisfy this condition. So first, we find the gradient of the total error function with respect to first parameter, and the same condition for the second parameter. And now, we need to plug in the values of x and y and solve equations 1 and 2 together to find b1 and b0 values. Now, let's make some calculations. Step 1. We need to calculate for each data point x squared and xy. Step 2. We find the sum of those calculated values. Step 3. The slope of least regression line is computed as follows, and in our case it's equal to 30.2. Step 4. We calculate y-interception of least regression line, which is equal to 162. And finally, step 5. The equation of least squares regression line is as follows. Y equal 30.2x minus 162. Let's have a look at this plot to see that linear least squares regression results in a good fit for the scattered data. Let's come back to our problem statement. We had to make a sales forecast, but some data was missing, and we had to find the approximate sales for those specific temperature values. And now, using the equation we have obtained, we can find the approximate sales values for those temperatures. The example we have considered has been modeled by a linear function, but what will we do if the underlying data cannot be represented with a line? Here comes nonlinear least squares regression that extends the linear one to a much broader set of functions. Just like linear regression, nonlinear is very sensitive to outliers. There are several advantages of nonlinear least squares regression, and the first one is broad range of functions that can be used to accurately describe different features such as asymptotic decay, rise, etc. Secondly, there is efficient usage of data. Good estimates can be performed with small data sets. On the other hand, there are some disadvantages, such as iterative optimization procedure and fewer tools for outlier detection available compared to linear regression. There are several common nonlinear least square regression models illustrated here, such as asymptotic regression growth function, logistic population growth function, and asymptotic regression decay function. Least square regression we have considered assumes equal variance in all data points errors. This condition is called homoscedasticity. When the condition of equal variance is violated, which is called heteroscedasticity, the weighted least square regression is used. To illustrate the weighted least square regression, let's have a look at this dataset. The variance increases with increasing x. As the company size increases, the revenue tends to diverge. In weighted least square regression, each data point has a specific amount of influence over the parameter estimates. The weights can be inversely proportional to the corresponding data point variance, so that points with lower variance will be given higher weights and vice versa. In weighted linear regression, the equation will be modified with weights added. For example, let's consider the equation of line we have seen before. In this case, it will be y weighted bar is equal to b0 x weighted bar plus b1, where x weighted bar and y weighted bar are weighted means. In most real-life problems, the weights are not known in advance, and they need to be estimated. And one way to estimate the weights is repeated observations at each value of the covariate vector. Although implementing weighted least squares might be challenging, it has some advantages, such as outliers can be down-weighted and data points can be removed by setting their weight to 0.